If you take out the galvanometers, you can kind of see that if you just drift it left and right, you can see the meters deflect all over the place. So it's very low friction needle attached that has a magnetic. But it's basically it's a little magnetic needle device. And when you attach it, and I forget specifically how it's attached, to a wire, and an electric current flows through it, without it affecting the current flow, and I say without, it's very, very minimal disturbance of the current that flows through this thing. The net result is that it will deflect left or right via the magnetic interaction between the current and this movement, or this magnetic needle. And using that information, the deflection is proportional to the amount of current that flows. Not only that, but if current flows in the opposite direction, the needle deflection will go opposite. So when we talk about measuring voltage, we talk about this idea of physical potential difference, what does it really mean? Well, on a basic level, what it means is there's a relationship between the movement of electric charge and the corresponding value that we can calibrate and measure. The movement of the electric charge, then, as it's calibrated to our device, then is related to, but not directly, what we measured when we say we're measuring the voltage, for instance, with our voltage sensors. In the end, it always comes down to the same thing. What do we really measure? We measure the flow of current, because the flow of current affects things magnetically. The flow of current affects things electrically in various ways. It always just comes back to what electrons are doing. So we live in a very simple, primitive world. Bare skins and bone dries. We can measure current. We can measure length. We can measure time, which really we use by measuring length in some basic level, or current. Very little else. We measure mass on a balance by measuring length. Temperature would be maybe another thing that might be more fundamental, but then how do we typically measure temperature? We measure the height on a thermometer, which always comes back to length. So for all of our fancy equipment and everything that we use in our world, it always comes back to somehow measuring movement of electric charge, or physically measuring length. I mean, if you think about that, it's kind of amazing what we can do with that. But it's no wonder we don't have a better sense of what quantum mechanics means to make up these weird ideas for string theory, because we can barely make simple primitive things. Oh, we figured out some great ways to utilize this. Now, I forget the name of this thing. It's got some damn French name, which is why I never bothered to remember it. The arm something. The arm and I don't know who the hell cares. Just kidding. Just kidding. Okay, so here's the idea behind an electric circuit in general. So what we refer to as an electric circuit is really a closed conducting pathway. Now that doesn't mean you can't detach it, but when we have a functioning electrical circuit, it's a closed conduction pathway. Electrically conductive pathway. So typically we take wires and attach it to something whatever. And in order to get charge to physically flow, put in a power supply. And the idea is when this thing is connected, the power supply, which is one of many number of things. It could be a chemical reaction happening in a battery. It could be the discharge of some capacitive systems. It could be alternating current coming out of a wall socket, which is usually stored in a capacitor, which was originally derived from mechanical energy to electrical energy transformation. But ultimately, we have some driving force which produces the overall potential, electric potential, voltage, if you will, that is what physically supplies the electric current through the circuit and also drives the movement of that current. Let's call this V for now. So that's basically it. The only question is what's inside this box and how do we analyze it? And ultimately, as engineers or scientists, what do we use it for? Or consumers, I suppose. So what we're going to focus on today is the measurement of these quantities. First of all, to begin with, and I'm going to keep this sort of in straight form, most of you have seen this, which is the idea of of Ohm's law. And we'll get more specifically into it on Tuesday. But the idea, ultimately, is that the electric current that will physically flow when you have a conducting pathway is directly proportional to the voltage or the energy difference per unit charge between the two ends of the pathway. Inversely related to, if you will, the drag forces that are associated with that conduction pathway. So if you think of a moving electron, and by the way, we call this the drag forces, we lump it together and refer to this ability of any conducting pathway to resist the movement of electric charge when you apply a voltage. We refer to that quantity as a resistance. So, on the surface, if we knew something about current and we knew something about resistance, we would ultimately be able to obtain this idea of voltage, if we could not directly measure it. So that's essentially the idea. If we looked at sort of a model conductor, and by the way, whether it's a good conductor or a bad conductor, we're always talking about conductors. If the charge can't physically flow, then it's not of much use in producing a electric circuit. Unless, of course, we're charging the capacitor. You still have to have charge movement. So, as a model of a conductor goes, if you have a certain voltage between the ends of a conductor, then you'll have the movement of an electric charge from one end of the conductor to the other. It's a positive charge, it will go from positive to negative. If you will, the charge will flow downhill in an energy sense, from high energy to low energy. One of the things that's sort of interesting about it, however, is we talked about the electric field associated with any potential difference over space. The electric field being related to the space derivative, in this case d dx, of the potential difference, how the potential difference changes from one side to the other, just like with a capacitor. As the electric field pushes or drives the direction of the electric charge by inducing or producing electric force, once the current is in motion, or once the charge is in motion, an interesting feature about it is that it has a terminal velocity. So physically plugging this thing together gives it movement. It gets the charge to flow. Basically, by pushing a charge in, the charge gets pushed out the other side. And the resulting movement of that charge is the potential difference, is what it's associated with this electric field. Now, once the charge is in movement, though, it has a very low terminal velocity because of the inherent drag forces that are associated with the conduction, or with the material that's allowing the conduction to flow. First of all, the movement of the charge really requires that you take electric charges, electrons if you will, off their atoms. You've got to have enough energy to pull them off the atom. But as they move along, they're constantly being attracted to the nuclei of all of the atoms that they come in contact with as they flow across. You have an atom, each of them has an electron. As you push this electron over, and this electron is pushed over, it's going to be suddenly attracted to this positive charge, which is going to impede its movement to keep going forward. But there's a lot of other factors, but ultimately, you've got a drag interaction that pushes in the opposite direction. So there's some kind of a drag force. And the resistance is related to the manifestation of this drag force per unit charge over time. So the question then for us is, how does this apply to any conducting pathway? In the simplest sense, if you have some driving power supply, that will set the voltage through the entire electric circuit. Kind of like going into a ski competition, a mountain defines a ski run. The only question is, how do you get from the top of the ski run to the bottom? It's set in place, but you've got various pathways from which you get to the top and the bottom. And as you go down, you utilize potential energy. When you get to the bottom, you no longer have as much gravitational potential energy. So, to this end then, whatever this voltage is that drives the entire process, we thought about it as a hillside. And you have an electric charge that's over here. Ultimately, it's going to go down the hill until it gets to the bottom. The bottom of the hill corresponds to the negative end of the power supply. Think about it as a positive charge. The various drops, if you think about this as being the x direction, if you will, as the charge moves across. The various slopes are related to the electric fields, if you will, between the various elements that are along the way within the electric circuit itself. So, we wanted to think about this thing, the slope of these regions corresponds to dV dx, if you will, for the electric field. Typically won't be able to graph, but what will happen is if you replace this something with something, R1 and R2. By hook or by crook, as the charge begins here at a high potential energy and a high electric potential, at the time it gets down here, it will have dropped whatever this voltage is. When it gets to the bottom of the hill, it's dropped in elevation. Every charge that flows from top to bottom will ultimately lose an amount of energy equal to its charge times V. That's how much energy gets lost, or the amount of work required to drive that particular charge around the circuit. Now, every point along the way, the drag forces associated with the conductor along that path will ultimately suck a little bit of energy out of the moving charge. Or, said a different way, lower the voltage ever so slightly. In the case of wires, wires typically have very low drag. That's why we use them as connectors. So typically wires have low drag, therefore low resistance. Usually to the point that it's negligible compared to everything else. So the biggest occurrences where the voltages drop happen across the various resistive elements, the various obstacles along the conduction pathway. So if we thought of this as having a potential difference from one side to the other, say from here to here, you're higher here than you are there, we could call this voltage drop maybe V1. And as a charge moves along and comes to the next serious obstacle, again, the wires do always have a subtle effect, but if they're in series with much more significant elements that cause circuit drag, they're negligible. And we can think about the potential difference across the next significant region, in this particular case, V2. Application of Ohm's law basically then would work something like this. I didn't want to talk too much today. I already told you I wasn't going to talk much. Here I am talking. I lied. So the idea then is the movement of this electric charge, which I'm going to call I, and it's it's dq dt. It's a rate of movement of electric charge across this region here, if we know its resistance and we know its voltage. The current would be related to whatever this potential difference is divided by the resistance. I'm going to call it I1, current flowing across this first part. You'll see why in a moment. There's a current flowing across the first part. Using what we know about the potential difference and the resistive drag across the second element, we could say that the current flowing across the second region is related to the voltage across that second region and its resistance divided by its resistance. Now, here's where a couple conceptual elements come into play. First of all, as the charge flows along, the sum of all of these potential difference drops, or these voltage drops, will equal the total voltage that physically drives the movement of the charge to begin with. So if this power supply is V, the sum of all of these other voltages, in this case V1 and V2, and we could say plus the tiny little voltage associated with the potential difference drops across these little wire elements. We wanted to add that. They should always add up to what the total voltage is that's pushing the current through. However you get to the bottom line, this is what we say call. And that's determined by the power supply. Here's the second thing. And this is true for any closed conducting pathway. If there was another pathway, there might be other things going on. If there's a second, whatever. Bottom line is for any closed pathway where you start and end up in the same point, and we would use 0, if you will, being the bottom of the hill. Take an elevator to the top of the hill, ski run, and then you go down the ski run, you end up back at the bottom. Now, nature doesn't have a credit card. Electric charge, once it's moving, has to always be accounted for. So, moving charge through here, out of the power supply, it's going to push all the charge in front of it, which is going to result in the circuitous, continuous movement of electric charge around the circuit. What that means, it's kind of like fluids, ideal fluids in fluid mechanics. It doesn't build up and store in various regions. Whatever flows out of the power supply on one end flows into the power supply on the other end at the same time. We can think of the electric charges as being, I put more charges here, marbles in a garden hose, if you will. So every time you push a charge in, it pops a charge out. It doesn't take time for an electric charge to go from one end to the other, and you're not measuring the same charge when you close the circuit. You're not measuring this charge coming out at this end. It may take minutes for an individual charge to get all the way around. However, as soon as one charge comes out, one charge goes in. And part of the reason for that is it has to do with how the chemical reaction inside the battery, if you will, generates its electric charge. So you have a highly controlled, completely balanced equilibrium of electric charge flow. It's always consistent, always the same through any single closed branch of a conducting pathway. So in a circuitous loop like this, whatever the current is here, it's going to be the same here. 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 And ultimately, it's one continuous flow. So around this loop, and it's a series loop, I is constant everywhere. Now, it won't necessarily be constant if we start branching things off, for sure. So we're not going to get too far into that. I just wanted to set the table and the context for what we're going to do today. So, the million-dollar question then for us is going to be essentially, how do we use current, voltage, and resistance in order to make definitive quantitative measurements of electric potential at various regions around an electric circuit? And to this end, let's make a note of a couple of points here. To measure a voltage or a delta V, between any 2 points. In a circuit. We would start by saying that the potential difference between those 2 points, and let's use this point here and this point there. So I'm going to call this A and I'm going to call this B. So the potential difference between A and B. That potential difference will be equal to the current that's physically flowing between those 2 points and the resistance between those 2 points. Whatever it is. It could be a single element, it could be multiple. You may not know what the hell is going on in between. But if you can measure the difference between the potential energy, or the electric potentials between these points, it will directly be related to that information there. Less positive. So this assumes free-flowing charge. So, how do we utilize this, and where does it come into play? We've already started to see how we measure voltages. What is it about voltages in terms of what's the technique for measuring the voltage? I got my voltage sensor, it's got a red and a black lead, and I want to measure the voltage across this thing, assuming it's an electric circuit. How do I need to plug these in? How do I need to measure these if I want to measure the voltage across this thing, or between this point and this point? How would I do it? You always want to measure a voltage in parallel. In other words, if I want to measure the voltage from here to here, then I'm going to take whatever I'm going to use for my power supply, or for my sensor, my voltmeter, and I'm going to connect it with the ends of my device. The ends of the device. I'm going to connect it across the ends between the 2 points that I'm interested in measuring. So, what that would mean, if I'm looking at R1 specifically, in this case, I don't necessarily know much of the information, but what I might know is that here's R1, and there's some current flowing through this. I'm going to call it I1 for now. It's I, whatever, but call it I. So if I want to know what's going on from A to B, I need to figure out how to measure across it. I don't want to measure in series with it, because then I'm not measuring the potential difference across it. I'm only measuring the potential difference between 2 ends of the wire along the same circuit. So it wouldn't be particularly helpful. So if I want to measure the voltage, I need to connect something in parallel to whatever it is, or whatever 2 points I'm trying to measure. And as soon as I do that, something nefarious is going to happen. Here's my little meter here. I'm going to bleed current off. As soon as I connect another conducting pathway in parallel with this resistance, that's going to open up the movement of electric current across this region. Well, there are potential problems. How much current flows across this region, and I've got current flowing across this region, I may inadvertently saturate my power supply's ability to produce electric current. If I do that, I'll disturb the current, and I'll disturb the circuit to the point that whatever it is I would be otherwise measuring, it would be of particularly no use. So one of the things that I have to consider, and these are the things always to think about, is I have to be non-invasive to the circuit. If I'm invasive to it, I will change its behavior just by the presence of making a measurement, in which case it's not particularly helpful. So I got to figure out a way to do so. Well, one way to do so is if I bleed some current off here, and I'm going to call it IM now. Well, one of the things that's going to happen is that back here, now the current that's going to be flowing into this region is going to be the combination of my original current plus this new current, the amount of current that's going to bleed off of it. Hopefully that's not enough to disturb other things in the circuit, but potentially it could be. So that's one consideration. Because if there's something else over here, now the relationship between voltage and current and resistance that regions around will no longer be the same. Okay? So the first thing that I have to do is I have to minimize this current. Easiest way to minimize this current IM, make this meter have a huge resistance. Everything's a equilibrium flow process, so that's why you have to be worried about this. To do so, the resistance of the meter itself, we want to make it large. And by large, I mean large relative to the rest of the circuit, large relative to this. Okay, that's the key. So Rm, in general, should always be very large relative to what it is you're going to measure. So, in order to do that, we got two different ideas. If I put a second branch in the pathway between A and B, I will actually increase the amount of current that will flow between those 2 points, all other things being equal. Because current's going to flow here, and current's going to flow there. If the voltage does not change significantly across R1, then I'm going to have more voltage, or I'm going to have more current because I'm going to have the same voltage across R2, or I mean across this voltmeter. This is positive, and this is negative. This positive and this negative will be the same.